We are supposed to find the inverse of each function. Number one, if you simply interchange x and y, then get y by itself using your algebra skills, you would get this function. Y equals 1/2 x minus 3/2. Let me fix my 2's a bit, because they are a bit ugly. Number two, if you do the same thing, if you interchange your x and your y, and then get y by itself. I'm going to subtract 4 from both sides. I'm going to divide each term by -3. Gives me negative 1/3 x plus 4/3. Subtracting a 4 divided by a negative is going to be subtracting a negative, which is the same thing as adding a positive. Then if we simply square root both sides, we get plus or minus the square root of negative 1/3 x plus 4/3 equals y. Number three, same process. Interchange your x's and your y's, and get x by itself. We're going to have to square root both sides. Remember, when you take an even root, it's plus or minus. To get y by itself, and that would add 2 to both sides. So we see we get these inverses for example, for the first problem set, 1, 2, and 3. Should be mentioned that this answer for number 2 looks a lot different on the answer key. It looks like this. These answers are the same. So don't freak out if you didn't get the first, or if you didn't get this bottom answer, it's fine. Doesn't matter which one you have. For 4, 5, and 6, find the inverse of each function, sketch the function and its inverse. Decide then if the inverse is a function by circling yes or no. So number 4, we got y equals the difference of x and 3 cubed plus 6. So let me go ahead and graph that first of all. Don't graph this yet. I'm going to do some things here. Let me just get this started out. This is what the parent looks like. Parent being y equals x cubed. If I take this graph, this says to subtract 3, that means this vertex, which is at 0, 0, goes to the right 3, 1, 2, 3. And then this plus 6 translates the whole thing up 6. 1, 2, 3, 4, 5, 6. Perhaps it looks something like this. So it's right 3 and up 6. I have an x-intercept and a y-intercept here. Should probably figure those out. Let's see what happens. To find this x-intercept, I'm going to put 0 in for y. To get x by itself, I'm going to subtract 6 from both sides. And I'm going to cube root each side. It's okay to take an odd root of a negative. I'm going to add 3 to both sides. So this is the x-intercept of this function. So I'm going to label that 3 plus the cubed root of negative 6, 0, which is obviously here. The y-intercept for this function I'm going to put 0 in for x. It's going to give me a negative 3 cubed, which is negative 3 times negative 3, which is positive 9 times negative 3 is negative 27. Add 6 to that, you get negative 21. It's really not great that I have all this work crowded together. But I don't think I gave you enough room to do all this work, so it's just going to have to work. So the y-intercept down here someplace of this graph, 0 and negative 21. So the inverse. I'm kind of doing the directions in an order that I didn't say to do it in, but it doesn't really matter what order you do it in. To find the inverse, I am going to interchange x and y, get y by itself. I'm going to subtract 6, cube root both sides, and add 3 to both sides. So how do I graph this? Well, the cubed root is the inverse of x cubed. Therefore, and once again, don't draw this yet, if the parent graph was this red curve, then this graph, since it's the inverse, is reflected over the line y equals x. So it is going to basically look like the following. Let me get rid of that stuff that's up there. So basically, instead of coming up like this, and don't draw this yet, it's going to look like this. This is simply the inverse of the parent graph y equals x cubed, which is y equals the cubed root of x. That's the inverse that's reflected over the line y equals x. Then this minus 6 translates this whole thing to the right 6, and this plus 3 translates this whole thing up 3. So be something like this. I'm going to draw this better to scale, like the other one is. So something like that. This vertex, once again, is 6, 3, which is perfect because notice once again, to find the inverse, you interchange x and y, and that's what's happened here. Also, that means that the x-intercept of this red curve would have been the y-intercept of the original curve. So this x-intercept is negative 21, 0. We don't have to show the work for it because we've already done the work for it. And then the y-intercept for the red curve is the same as the x-intercept for the white curve. So that is 0, 3 plus the cubic root of negative 6 and one thing that spells bad mathematics, bad teaching, is when you're given too much work to do in a small space. So I apologize, this is on me. It'd be better if these things down here weren't in the picture. Alright, number 5. Let me scale this back a little bit so it's not up in my way. Before we get to number 5, let me just point out again, when you graph a function and its inverse, any place one function hits the line of symmetry, the other function should hit it in the same place. This white and red curve should be mirror images across this yellow line of symmetry. And if you look at it, it looks pretty close. Not perfect, but pretty close. Alright, number 5. This graph, real simple. It's a parabola. And don't draw this yet until I move it. It's a parabola whose vertex is at the origin. This minus 4 takes the entire graph and translates it down 4. 1, 2, 3, let's say that's 4. That's 0 and negative 4. Y-intercept is obviously negative 4. X-intercepts, let's see if I can do this maybe in this location. 0 equals the difference of x and 4 squared, square root both sides, and add 4. And it tells me I have an x-intercept of 4, but only one x-intercept, which means I have definitely messed up this problem. Here's where I messed it up. This minus 4 translates the graph to the right 4, not down 4, which is consistent with this saying the x-intercept is 4. I apologize for that. So, made a mistake, and knew I made a mistake because when I did this x-intercept, things just didn't work out correctly. So I need to find the y-intercept. This work is actually completely unneeded, other than the fact that it helped me find my mistake. To find the y-intercept, I'm going to put 0 in for x, which is going to be negative 4 squared, which is positive 16. So this y-intercept is positive 16. Just have to find the inverse of this function. And interchange x and y. Square root both sides. When you take an even root, it's plus or minus. So this is my inverse function. So if the original parent graph, which is a parabola, vertex at the origin, opening up, that's reflected of a line y equals x, then it's going to look like something like this. Don't draw that yet. And then this plus 4, this moves the graph, translates it up 4. Positive of that. I'm going to make the same mistake twice. Let's say that's up 4. So that puts me at 0, 4 for the y-intercept. My x-intercept has to be the opposite of the y-intercept for the white graph. It is at 16, 0. Something I forgot to do for 4 and 5, part of the directions, is the inverse of function. Circle yes or no. So looking at number 4, is this red curve a function? Yes. If you run a vertical line over it, you will not hit it twice. Number 5, is the green curve a function? No. Does not pass the vertical line test. If I were to run a vertical line, it would hit this in 2 different locations, which makes it not a function. Oops, pardon me. And back for number 6 here. Graphing this function. It's a parabola. This plus 2 translates it up 2. It's fairly simple. Fairly. Vertex is at 0, 2. No x-intercept, so it does not cross the x-axis. So I don't have to show any work for the x-intercepts. The inverse of this function, interchange x and y, and I get y by itself. So it's this white graph reflected over the line of symmetry. So it looks a little something like this. Should be the same width, if you will, as this graph here. I didn't draw this wonderfully. Maybe a little more like that is more accurate. And this x-intercept is 2, 0. It's the opposite of this one, opposite of that y-intercept. If you look at this, this plus or minus square root means it's the inverse of the parent graph, and then which means it's reflected over the line y equals x. And this minus 2 translates it to the right 2. Is that blue? I don't know why I keep doing that. Is the blue graph a function? No, it does not pass the vertical line test. If I run a vertical line, I'm hitting it in more than one location, which is not good. Number 7, for each parent graph, describe the transformation or transformations that have taken place in the related graph for each function. Well, this graph here is a parabola that opens up, looks like so. Doesn't really matter what it looks like, but that's what it looks like. Y equals plus or minus the square root of x, that's the inverse. If it's the inverse, it's the same graph as this yellow one, but it's reflected over the line y equals x, so it looks like this, which is not answering the question. Answering the question is, this is reflect over the line y equals x. That's it. B, same thing. It's plus or minus the square root, so it's reflect over the line y equals x. This minus 3 in here translates the graph right 3. Number 6, plus or minus square root. It's the inverse of the parent equation. Therefore, it's reflected over the line y equals x. This plus 6 translates the graph up 6. 6 units to be more specific. D, a couple of things happening here. Please recall that if you have stretches, shrinks, which are called dilations, and you have reflections, shrinking and stretching happens first, dilations are second. So D, we would say this is stretched vertically by 3, you know it's stretched because this coefficient, it is bigger than 1, its absolute value. If it's between 0 and 1, then you say it shrinks it vertically. And this plus or minus the square root, once again, that reflects the graph over the line y equals x. E, this point 2 is first, plus or minus square root is second, and then adding the 4 is the last thing that we do. So we are going to shrink the graph vertically. By 0.2. We are going to reflect the graph over the line y equals x, and we are going to translate the graph up 4. F, we are reflecting over the line y equals x. That's from the plus or minus square root. This minus 5 translates the graph to the right 5. This plus 3 translates it up 3. So we're going to translate right 5 and up 3. Number 8 here, this graph, it's a little something like this, y equals x cubed. And the cubed root of x is its inverse. It looks like this. So this here says it's the inverse. Anytime you have a graph and its inverse, the inverse is reflected over the line y equals x. So this is reflect over y equals x. In fact, that's got to be true for each of these. Because if you look at each of these problems, they have cubed root of x in it. So I'm just going to do that right now. Save myself some time. Doesn't save you any time, but it saves me some time. This one here on D, the reflecting happens after the dilation. So I need to leave a space for that, say what that 0.04 does. 0.4, I should say. Alright, so I got all that part done. So what else is happening in these graphs? A, nothing else. Everything else is the same, so nothing needs changed. B, this plus 6 translates the graph up 6. C, this minus 4 translates the graph right 4. D, what does the 0.4 do? We're multiplying that times our function, so it's going to shrink or stretch the graph vertically. If this number's absolute value is between 0 and 1, then it shrinks the graph vertically. So we'll say shrink vertically by 0.4. E, we have two translations. This plus 3 translates it to the right, and this minus 8 translates it down. So we'll say translates, I think I said to the right, it's to the left. Translates to the left 3 and down 8. Finally, F, got a couple different reflections here. So we have the reflecting over y equals x, because the cubic root, we have this negative out in front that reflects the graph over the the x-axis. The order that you do those reflections doesn't matter, but they need to be before the translations. We're going to translate right 3 and up 6. Right 3 because of this, and up 6 because of this. In Beth's physics class, the lab work score counts the same as a test score when the grades are averaged for the quarter. So in other words, a lab score and a test score, there's nothing to distinguish between those two. Equal in importance. No other scores are used to find the average grade. She scored a 75%, 80%, and 72% on her tests. What lab score must she receive to average an 80% for the quarter? Let's talk about these percents. Let's say that she only had 3 grades, the 75, 80, and the 72. If we took those and added them together, and then divided that by 3, that would give us her average grade. That's just the mean. Adding up all the numbers you have, and then dividing by how many numbers. So it's a situation that we have here, but then she's going to take one more test. So what is she going to get on this test? We don't know. So we'll call that an X. So off to the side, X says what lab score must she receive. So X is the lab score. That's the lab score that she needs. Well, now we're adding 4 numbers here, not 3. So its denominator should not be a 3, but it should be a 4. And these should average, she wants an 80%. So adding up these 4 numbers, dividing it by 4, it should give us an 80%. So if we were to do a couple of things here on this first step, if we were to multiply both sides by 4, on the left the 4's cancel. On the right, 8 times 4 is 320%. Also, here on the left, we're going to combine like terms, 75, 80, and 72. 75 and 80 is 155. 155 and 72, I believe that's 227 plus x. Just combine like terms, 227% plus x. To get x by itself, subtract 227% from both sides, and we get x equals 93%. So what lab score must she receive to average 80% for the quarter? Beth must receive a 93%. Ten, 11, and 12. Graph the 2 relations on the same screen on your calculator. Copy the graphs below, showing little regard for accuracy. That means don't spend all day translating the graphs. Determine if the 2 relations are inverses. This is just by sight. There should be no work to do to determine that. Circle yes or no. If the answer is no, so that means if they're not inverses, write the equation that is the inverse of the first function. So in other words, for 10, 11, and 12, graph both of the functions quick as you can using your calculator. Then, if they're not inverses, find the inverse of the first function. So if they're inverses, you have no work to do. If they're not inverses, you have the work to show that they're inverses. To find the inverse, I should say. For 10 here, let me pull up my calculator. I'm supposed to put both of these in. So I go to the y equals, and I type in parentheses x plus 1 quantity squared. And then for y sub 2, since there's no plus or minus button on my calculator, I have to put in the plus version. And then when I'm done, I'll put in the minus version. I forgot my radical here. Let me go back up here to the beginning. Second insert, second square root. There we go. And then for y sub 3, I type in the negative version of that. Negative second square root x minus 1. Graph, I can see those are my curves. So it's looking something like this. And the other one maybe like this. Are those graphs symmetric with respect to the line y equals x? No, they're not. Therefore, they are not inverses of each other. not inverses. If they're not, you're supposed to find the inverse of the first function. To do so, interchange your x and y. Get y by itself. Now if I get to the end of this, and this is the same equation as what was right here, it means I made a mistake and it actually is the inverse. But that is not the case. So this is the true inverse. It has the negative on the outside of the radical, where number 10 had the negative 1 on the inside. Number 11, let's pull up my calculator here again. y1, I got x squared minus 2. And then for y sub 2 and y sub 3, I'm going to have x plus 2 inside the radical and an x plus 2 inside the radical with a negative on the outside. Looks like it has potential being inverses. Let me just cheat. And I cheated and I lost it. There it is up here. Are these graphs inverses? Sure looks like it. It looks like if I were to draw this line of symmetry here, that those graphs are identical on both sides. So I'm going to say, pardon me, I just flipped to a page there. I'm going to say yes, these are inverses. Last part of the direction says, if they're inverses, you're done. So I don't need to check to see if the first one is. If I have any doubt, then you would just find the inverse of the first one and see if it is the second one. I don't doubt it, so I'm just going to leave it at that. Should label these. This is this curve here. Was y equals x squared minus 2. This curve here was y equals plus or minus the square root of x plus 2. Number 12, put this on the calculator once again. I got x cubed minus 5. And the cubic root of x, which there's several ways to put this in. Quickest way for me is just to type in x to the 1/3. If you do it this way, make sure you put the 1/3 in parentheses. X to the 1/3 is the same thing as the cubed root of x. I'm sure someplace buried in this calculator is a cubic button. So I graph these. And these do not appear to be inverses. Let me grab this and throw it on here. So let's look at this a little more closely. So right now I'm saying no. If I draw this line of symmetry, which is approximately here, this point where they're hitting each other, intersecting each other, needs to happen on this line of symmetry, and it doesn't. These are not mirror images of each other. So find the inverse of this first function, interchange x and y, get y by itself, cube root both sides, and this is the true inverse of that first function. I gotta make sure I label these functions. I got two on the same coordinate plane. Y equals x cubed minus 5 is this one down here. Y equals x cubed minus 5. This one up here is y equals the cubed root of x plus 5. 13. Find a function that is its own inverse. Can you find more than one? What this question is basically asking you, find a function that is symmetric with the line y equals x. Because if it is symmetric with it and you reflect it about that line of symmetry, you're going to end up with the same graph. Here are two obvious ones. Y equals x and y equals negative x. Y equals x is on the line of symmetry, the entire line. If you reflect it over itself, it ends up in the same spot. Y equals negative x looks like this. If this is reflected over the line y equals x, it's just going to take this green part and put it where the red part is, and it's going to take the red part and put it where the green part is. But to answer the question the way it is asked, find a function that is its own inverse. Found it. Can you find more than one? Yes. That's a terrible question. The way that's worded, all you have to do is say yes. You don't even have to find another one. It's implied to find another one, but it's not your job to go for things that are implied. But it would be y equals negative x. The Denison Fire Department must purchase a pump that is powerful enough to propel water 80 feet in the air. So this is what they want. They want it to go 80 feet in the air. One pump is advertised to project the water with a velocity of 75 feet per second. The velocity of the water can be described by this equation. V equals the square root of 2 times g times h, where v is the velocity of the water, g is the acceleration due to gravity, and h is the maximum height of water flow. Before we get into the questions, let's make sure we define our variables, put them all together nicely. V is velocity, g is acceleration, which we're told is 32 feet per second squared, and h is the maximum height. Part A, write the simplified equation after replacing g with 32. Well, we simply say v equals square root of 2 times 32 h. 2 times 32 is 64. Square root of 64 is 8. Square root of h, we don't know. This is the simplified equation. V equals 8 times the square root of h. Graph the relation. The parent graph for the square root of h looks like this. This 8 takes that graph and stretches it vertically by 8. Maybe something like that. Does not change the vertex. C, use the graph to find the maximum height of the water from this pump. Well, to do that, from this pump, it's referring to the pump that's advertised at 75 feet per second is the velocity. I'm not going to use the graph to do that. I'm going to use part A to do that. Velocity 75 feet per second. Get h by itself, I'm going to divide both sides by 8. And square both sides. I use my calculator here. 75 divided by 8 9.375, which is 9 3/8. And then I'm going to end up squaring that So I'm going to hit second answer, which means you're going to take the previous answer in the calculator and throw it up there. Throw it up, not as in vomit throw it up, but throw it up as in, it's going to use that number. Square that, and get 87, let's say 87.9, that's rounded, even though I hate to round. So 87.9. So if I square both sides, we get 75 over 8 squared, which once again was 87.9 approximately. What's the maximum height of the water? About 87.9. D. Does this pump meet the department's need? The department needed it to go 80 feet in the air. This is going more than that. Yes. Yes, it does. E. Another pump is being considered that propels the water with a velocity of 70 feet per second. Will this meet the department's needs? Well, we change the 75 here to a 70 feet per second. Divide both sides by 8. Square both sides. I throw that into my calculator. 70 divided by 8. And then I square it. 76.6 approximately. Will this meet the department's needs? No. Because it, let's say because its height is 76.6 feet. I feel like an idiot writing this. It's just such an obvious sentence. Which is less than 80 feet. This pump can propel the water 76.6 feet high, but they need 80, so of course it does not meet their needs.